called federated averaging from a stochastic, from a gradient descent perspective. So this algorithm is called federated averaging, and it's in its original formulation, federated averaging is used to learn a single model, or this is for this algorithm is used in a single model setting. So we want to learn a linear model again. So we focus on linear models, or the parameter vectors, parameters of the linear model. But we want to learn, or we want to use these parameters for all nodes in the local data, in the empirical graph. So each node should end up with the same local model parameters. In some application, it's useful to learn to train a single model, but from distributed data. Does any one of you have an application in mind where it's useful to not learn different models for different local data sets, but learn one single model that is used for all local data sets? No, for example, healthcare. If you don't consider personalized healthcare applications, but plain basic healthcare, you want to learn a predictor for the risk of a heart attack from basic characteristics like age, body weight, body height, and you want to train this model from as much data as possible, like the data sets that are stored in hospitals. But of course, you cannot share raw data between hospitals, so you need to train this model in a distributed fashion. And this is something federated averaging can do. And it's actually closely related to GTV minimization. In particular, we can formulate federated averaging as the problem, or as an optimization problem. Again, we want to minimize the average or the local loss at each node. So the local loss is the same as before, a local loss for a linear model. Note that we have now a separate model parameter for each node. So how does this go along with training a single model? Well, we enforce that they are all the same in the constraints. So we want this Wi, these local parameter vectors, to belong to a certain subset, and this subset is given by all stacked parameters that contain constant, or that contain identical local parameters. So this with some block C, d-dimensional. So this C can be arbitrary, but we copy it, we clone it at all nodes. And this defines a subset or a constraint set. Okay, so I should be a bit more careful, more precise with the notation. I mean, the constraint is that the stacked local parameters stacking into one vector, one big vector, belongs to this subset. Okay. And yeah, so this is a problem of minimizing a convex. Again, it's a convex quadratic function subject to constraints. And how can we do this? How can we find the minimum of a convex quadratic function subject to constraints? Using projected gradient descent. And if you write down these projected gradient descent iterations, you obtain first of all, so one iteration of projected gradient descent consists of two phases. In the first phase, we update at each node locally the local model parameters at iteration k using a gradient step. Gradient step. And then what comes after the gradient step in projected gradient descent? So this is the local gradient step. And in the next phase, we project. We project into the constraint set. And this projection results in each local parameter vector being identical for all I and being given by the average. So this averaging. And this is also where the name of the algorithm stands from, federated averaging. So this is the projection. Projection turns out to be an average. Okay. Yes, and this is actually only one variant or a variation of federated averaging. And you also find in the literature another variant of federated averaging, which replaces this local gradient step by let's say a more powerful update. If you remember in the last lecture, in the gradient methods lecture, I pointed out that this a gradient step is actually a minimization problem, which minimizes a local linear approximation of the function plus some regularization term that keeps the update close to the current estimate. And we can do this similar here, so we can replace the local gradient step with a proximal step. So the resulting update is of the form of a proximal step, proximal mapping, which looks like this. So the next or the updated parameter vector at node I is solution of minimization problem. So we optimize. Of course, we want to optimize the local loss. So there must be somewhere the local loss again. But we also need to ensure that the update is not too far away. We don't want to make a too big of step or jump because we only approximate local approximations. We only minimize approximations locally. So this keeping the updated one in a local neighborhood is enforced by adding a second term here in the objective function, which measures the distance of the update from the current parameter vector at node I. So this here ensures that update stays close. Okay. And yeah, if you now replace this local gradient step in this two phases, in the first phase of projected gradient descent, you end up with what is widely known as federated averaging, and which I have summarized in the lecture notes in algorithm 5. Okay, yeah, that's all what I wanted to tell you about federated learning algorithms. I also encourage you now to carefully read over the Sorry, there are some questions which I like to take. So the questions are, is there some difference between using this constraint and making a single matrix containing all data sets? I guess this question was related to this federated averaging. Yeah, good point. So in this, when we implement this, we don't have to exchange raw data. We don't have to exchange raw data, but only these model parameters. So we only pass around model parameters across the clients in the empirical graph. We do not share raw data, and this kind of this avoiding the sharing of raw data is what prevents this basic approaches to collect all data and then run a single machine learning model on a laptop. I hope that this addresses the question. So please let me know if there are still some it's still unclear. Then another question: is this approach equivalent to the method when alpha tends to infinity? Yes, very good point. So instead of enforcing that all local parameters are the same by requiring them to be in the constraint set, we could avoid this constraint set at all and say we use GTV minimization. So we use alpha times the sum over the edges, and choosing alpha large enough will press the solutions of GTV minimization to be approximately constant. Yes, this also works. And this might actually be quite useful because this works works for any empirical graph as long as it's connected. So it's a very low requirement. You can get a connected graph with few edges. Yeah, by the way, question. Let's say you have n nodes and you want to connect them with a minimum number of edges. What's the minimum number of edges that you need to use in a graph such that it can be connected? Or let's say, what's the minimum connected graph? What's the smallest connected graph for n nodes? Nodes minus one. Yes, excellent. And what kind of graph is it? Do you also know some structural properties?
There's going to be one kind of a center node to which all the other nodes are connected.
Yeah, so one example is a star graph. Yes. Are there other graphs which are not stars, that have n-1 edges and are connected? For example, like this. Oh, this is actually wrong. This has n nodes. This is a cycle. I don't need this here. One less. Single path graph, yeah, or trees. I think if I remember correctly, trees is also a name for minimal graphs that are connected. Okay. Yeah. Any other questions at this point?